Okay. All right, so we are making our way into Chapter 3. And in Chapter 3, the topic is numeric summaries, or at least today's topic is numeric summaries for numeric data. Okay, and so, the idea behind a numeric summary is that you might have lots of data. Okay, so here's the big idea, is that your data might consist of, hundreds of observations. Hundreds or thousands of observations. And we might not be interested in knowing the details of all hundreds or thousands or however many observations we have. We might want to just summarize this, okay? And so with a numeric summary, we just boil down all of these hundreds or thousands of observations just down to one or a few numbers, okay? We may not want all of the details, so we ask for summaries. Okay, and so the summaries, the numeric summaries, or we might call them sample statistics, will, quote, boil down the data to just a few numbers. I hear this electrical humming. Sounds rather ominous, but I think we'll be okay. Stats 10, week 2, Wednesday. Okay, and so here's we have a numeric summary that I'm sure you're all familiar with. So here's an example of a numeric summary to illustrate its usefulness. Its utility. All right. So a numeric summary that you're probably all familiar with is your GPA. Okay? GPA is a single number, and this single number is supposed to summarize your academic career, right? Am I wrong in saying that? That's kind of the purpose of the GPA, right? It's a single value that is supposed to summarize your academic career. Right? And does it kind of do that? It kind of does do that, right? Does it tell the full story? No, okay? And so, if we were to look at your entire transcript and go through each quarter, you can probably tell me, like, oh, for this class I had this teacher who was really harsh, and that's why I got a low grade. Or, in this quarter, this was going on in my life, and I couldn't focus on my academics, and that might be why I scored poorly or whatever. We might all have a story behind every single one of these grades. But, if you are a admissions officer at a university or a graduate school or something, you might not be interested in all of the details when you're trying to make quick comparisons across thousands of students, okay? And so in that regard, the GPA is useful in that this single number does give us a picture of a student's academic career, okay? So it cuts both ways. It's useful in that it summarizes things, but when you get a summary, you lose the detail, right? So it does not tell the whole story. But it does, is useful to make quick comparisons. Okay. And so, you know, you have the GPA, but when you have something where the utility is so good, then you a lot of times after these summaries get established for what they are, you often have people trying to, quote, game the system to inflate whatever it is that we're looking at. So for the example of the GPA, I imagine in your high school, you know, your honors classes were scaled on like 1 to 5 and your regular classes were 1 to 4 or something like this. I don't know if this sounds familiar. And then so that kind of like took away a motivation to take anything that wouldn't count as an honors class, and you wouldn't want to take driver's ed via your high school. Does this even like, am I just making this up? But okay. Well, anyway, as far as the GPA goes, you know, we have people try to, quote, game their grade point average just to look better. Okay, and that's kind of the pitfall of using a numeric summary for too much, okay? If we're, you know, if we are looking at, you know, someone might set a goal and say, you know, we want to decrease unemployment numbers, okay? And this is the numeric summary that we're looking at. We're going to look at the unemployment rate. What you might find is that at different counties, they might start to try to, quote, game the system in classifying people who should be considered as unemployed. They might classify them as something else just to lower that unemployment number. So they might say, oh, you know, this is a special case. This doesn't count as unemployed. This counts as something else. And that's what happens sometimes with numeric summaries. But they are still very useful to make quick comparisons, okay? And we have a few numeric summaries that can be used for any set of numeric data, okay? So numeric summaries for any set of numeric data. And we have summaries for describing center, and that would be the mean and the median. And we're probably already familiar with some of these things. And we have summaries for describing spread or dispersion. And that would be the standard deviation / variance, okay, and the IQR, which stands for interquartile range. Okay. And these will give us a sense of the center of our set of data and the spread or dispersion of our data. Okay, and so according to our textbook, and so I'll just say some say that if your data is skewed, use the median and the IQR. Because they are not affected by extreme values. What does it mean to be skewed left? Yeah. Skewed left would be, this would be skewed left, right? So skewed left, we have extreme values on the high side or on the low side? Low side, right? We have extreme values down here. Okay, whereas, you know, most are up here, okay? The median and the IQR are not affected by extreme values, okay? And then if we say if your data is symmetric, you know, we may prefer to use the mean and standard deviation. I don't. My drawings are no good today. Okay. But the truth is any of these numeric summaries can be used for any numeric data set. Okay. So these might be preferences or guidelines. But we'll say any of these numeric summaries can be used for any data set, numeric data set. Okay, so first we'll talk about the mean and the standard deviation. We'll see how far we get in the lecture. We'll talk about the mean and the standard deviation, and then we'll talk about the median and the IQR. Okay, so let's just imagine a family. Okay, let's give this family a name. Imagine the Johnson family. Okay. So the Johnson family, they have 4 children. The ages are 16, 15, 14, and 2. Okay. So we can imagine a story for the Johnson family. And just looking at these numbers, would you say the ages and the Johnson family are skewed left, skewed right, symmetric? What do we have? Skewed left, right? Okay, and then and let's create a dot plot. So let me just start at 0, 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay. And then so I'll put a dot right here at 16, a dot right here at 15, a dot at 14, and a dot here at 2. Okay? So the mean has the symbol x bar. Okay? And we calculate the mean by adding up each x value. This is the summation symbol. Add up the x's, divide by n. I think we're familiar with this concept, right? Add up the x values and divide by your sample size. Okay, so as far as the mean goes for our data set, we would add up our numbers. We would go 2 plus 14 plus 15 plus 16. I get 47. I divide that number by 4, and I get 11.75. So my x bar all right, and our conceptual definition is that it is the balance point of our data. So if you imagined our dot plot to be a seesaw, and I wanted the dot plot to be put a fulcrum somewhere so that this thing is balanced, the place where I would put the little triangle or the fulcrum will be right here at 11.75. This is the mean. 11.75, this is our balance point. Okay. Now, looking at this data, if somebody said, oh, you know, the Johnson family, they have 4 children, and the average age of those 4 kids is, you know, just under 12 years old. Does that really tell the whole story of what's going on in the Johnson family? No, not really, right? And if you were trying to describe what the ages of the kids in the Johnson family would be, you would not be able to tell the whole story without pointing out the fact that there's one child who's much younger than the other children, okay? You'd have to say, you know, he's got 3 kids, 3 teenagers, or they have 3 teenagers, you know, around 14, 15, 16, and then they have a 2-year-old, okay? Otherwise, you know, if you just say the average age is around 12, that doesn't really tell the whole story either, okay? So, so here, you know, we see that for the skewed data, using the mean may not be the best, may not illustrate the whole picture, okay? Okay. If, on the other hand, there was another family, okay, just let's say the Smith family, and they had 4 kids, and their ages were 13, 14, 15, and 16. So here we've got okay, so this would be an example of some symmetric data here. You know, the mean here would be 14.5. You add these numbers up, you get the mean 14.5. This is where our balancing point would be. Okay. And as far as the Smith family goes, it seems like using 14.5 as the average age does an adequate job of describing where the kind of the central tendency is, center of our data is, okay? Okay, so the mean describes the center of our data, okay, by using the balancing point. And comparing the Smith family and the Johnson family, we can see that the mean was affected by the extremely low value. Okay, so the mean is, quote, pulled in the direction of extreme values or in other words, is pulled in the direction of the tail in skewed data. Let's, so we'll keep talking about summaries that we can use for skewed data. Not sorry, skewed data, for symmetric data. And the other aspect is describing the spread, okay? So we might want to describe the spread of a set of data, okay? And so to illustrate this concept of spread, I want you to kind of picture 3 different rooms. And the aspect that we're looking at is the ages of people in the room, okay? So think of the ages of people in a room, okay? So first we're going to visit a second grade classroom, okay? Just the students, okay? So if we think of the ages of the kids in the second grade classroom, are we going to see much spread in the ages? Okay? What kind of ages will we see in the second grade classroom? They're all going to be around 7 years old, right? 7 years old. You might have a couple 6-year-olds, you might have a couple 8-year-olds, but by and large, almost everyone's going to be around 7 years old, okay? Maybe a few 6-year-olds or a few 8-year-olds, okay? But nearly everyone, nearly all will be about 7. Okay? So as far as the spread in the ages, there's not much spread, so there's very little spread here. Very little spread in the ages here. Okay, what about this classroom? Okay, so not including me, but as far as the students in this classroom goes, okay, how much spread do we have in the ages of students in this classroom? Yeah. So as far as the ages go, okay, we're going to have more spread than the second grade classroom, right? So more spread than the second grade classroom. Okay, and then I would say, probably 90% of students, 90% in this class will be between, probably 18 to, 23, okay? And, we're going to have a few people outside of that range, but by and large, probably we can get about 90% of people within a 5-year span, okay? So about 90% in a 5-year span. So I would say, a moderate amount of spread. Okay. All right, let's say we go to the DMV waiting room. Okay. And we look around at the ages of people in the DMV waiting room, okay? What kind of ages will we see there?
16 to 85.
Yeah, we'll see lots of ages, right? We'll have teens, okay, young adults, middle-aged people, seniors, anybody who's driving, we'll even have kids of the middle-aged people, right? So, even some young kids, because they're they're accompanying their parents. So we have a high amount of spread as far as ages go. Okay. So if you have, you know, a lot of different ages, that's going to be high spread. Very few ages or very few different numbers represented, that's going to be low spread. So low spread means the values in the data are very similar to each other. So that's what we have in the second grade classroom. The values that we see are all around 6, 7, 8, most of them being 7. Okay? High spread, the values in the data are quite different. All right, so does this concept of spread make sense? Okay, so rather than just using these vague terms, little spread, moderate spread, high spread, okay, the standard deviation is a way for us to quantify the amount of spread. So we can say in the second grade classroom, the standard deviation is half a year. In this classroom, the standard deviation is maybe 2.5 years. And in the DMV waiting room, the standard deviation is maybe 15 years, okay? Or maybe, I don't know, something like that. It's just it's a way to quantify the amount of spread. Rather than just saying lots of spread and little spread, we can say, oh, the standard deviation is 5, the standard deviation is 25, or 100, or something. And that will give us an idea of how much spread exists in our data. It assigns a number to the amount of spread. That's the big picture and important concept behind the standard deviation, okay? So standard deviation is a value that quantifies the amount of spread. Okay, so this is our big picture idea, okay? Standard deviation is a value that quantifies the amount of spread. We don't want to, I'm going to give you kind of some ways to calculate the standard deviation, but we don't want to lose sight that the standard deviation is just a way to quantify the amount of spread here, okay? So when we define the standard deviation, it often is helpful to talk about the variance too, okay? So first I'm going to just say the standard deviation is equal to the square root of the variance. And the variance is equal to, I'm going to put this in quotes, the quote-unquote average squared distance from the mean. All right, and so the standard deviation, symbol for standard deviation is S, and for variance it is S squared, okay? Okay, so let's just do a quick check here. So let's say we have the Baker family, and they have, let's say they have 5 kids. Average age is 9. And the kids in the Baker family are 1, 5, 9, 13, and 17. Okay? All right, and then let's say we have the Thompson family. again, 5 kids, average age is 9, and the ages are 7, 8, 9, 10, and 11. Okay? So you could imagine what life is like in the Baker family and what life is like in the Thompson family. Both of them have 5 kids, and both of them, the average age of the kids is 9. But let's ask a quick clicker question, okay? If we calculated the standard deviation, and we're not going to do, we'll do this in a moment here, okay? But is the standard deviation for the Baker family, is it greater than the standard deviation for the Thompson family? Or is the standard deviation for the Baker family less than the standard deviation for the Thompson family? Or is the standard deviation for the Baker approximately equal to the standard deviation? We'll just say equal to the standard deviation of the Thompson family. Okay, so your answer choices, as soon as I fire this up, will be A, B, or C. Okay, and how do I do this? Okay, start a new multiple choice question. Go ahead, choose. Is the standard deviation for the Baker family going to be greater than, less than, or equal to the standard deviation of the Thompson family? Okay. You guys can discuss during clicker questions, okay? So during clicker questions, if you're not sure, you can turn to your neighbor and discuss why you think it is. It seems like by and large most of you are in agreement with what you think it is, but we'll go over our answers. Okay, I'm going to close the poll in about 10 seconds here at 1 minute. I think that's enough time. Okay, so if you haven't clicked it, make sure you click your remote right now. In 3, 2, 1, we're closing the poll here. Okay, and let's see. And the correct answer choice is A there. Okay. Oh, you know what? I have to designate there. So it seems like 99% of you agreed that the standard deviation for the Baker family will be larger than the standard deviation for the Thompson family, and that is correct. Okay. So that is the correct answer choice. And because we can see that as far as the Baker family goes, the ages of the children are more spread out than they are in the Thompson family, right? The Thompson family, the kids go 11, 10, 9, 8, 7. They're all very, very close to each other in age. In the Baker family, they are spaced out. They seem methodically spaced out about 4 years apart there, okay? All right, so let's go ahead and we'll calculate the standard deviation for the Baker family. Okay, so for the Baker family, okay, so the kids' ages are 1, 5, 9, 13, and 17, okay? And I gave the kind of this definition of the variance to be the, quote, average squared distance from the mean. Okay, so let's use that to figure this out, okay? We said that the mean age is equal to 9, and if you don't believe me, you could add these up and divide by 5 and you'll get 9, okay? So we want to know, what is the distance from the mean 9? Okay, how far is 1 away from 9? It's 8 units away, okay? And so one way we can do this is to calculate distance is you just subtract whatever number you're looking at, and we would say 1 is 8 units below. How far is 5 from 9? It's 4 below, okay? How far is 9 from 9? It's right there, distance is 0. How far is 13 from 9? It's 4 away. And how far is 17 from 9? It's 8 away. So these are the distances from the mean, okay? Distance from the mean. Now we could have, now we'll look at the squared distance, Okay? Anytime you square a number, they become positive. So negative 8 squared is 64. Negative 4 squared is 16. 0 squared is 0. 4 squared is 16. 8 squared is 64. So these are the squared distances from the mean. Okay? So the variance is defined as the average squared distance from the mean. Okay? So as far as the average goes, if we were to calculate the average, we would add these up and divide by 5. Now I have average in quotes here, and that's because we're going to add these up, add them up, and divide by n minus 1. Okay? So we would do 64 plus 16 plus 0 plus 16 plus 64. And we have a total of 5 numbers, so we're going to do 5 minus 1. So this gives me 160 divided by 4, and we get 40. So my variance is equal to 40. All right? You might wonder why we're using n minus 1 rather than n, why the average comes this way. The answer is it's a little complicated and beyond the scope of our course, but for those who are interested, you can go on Wikipedia and look up something called Bessel's correction. This is why we use n minus 1. And it stems from the fact that the variance is actually the average square distance from the mean in the population, but we don't know the mean in the population. We're using the mean of our sample as a guess for what the mean in the population is, and because our mean comes from the sample, it introduces some bias. We use n minus 1 to correct for that. If that didn't make any sense, don't worry about it. Just remember we use n minus 1 here, okay? So this is the variance, and so our standard deviation is the square root of the variance. And so we get the square root of 40, which is like 6 point something. Square root of 40 is 6.3246. 6.3246. Okay? And so we would say the standard deviation of ages in the Baker family is 6.3246. Okay? And there you have it. If we went to the Thompson family and calculated the standard deviation of ages there, perhaps, I don't know. Let's see. Can I flip the page here? Okay. So we'll go ahead and we'll do the Thompson family. We have, I believe, 7, 8, 9, 10, and 11. We're going to say the mean is 9, right? So we're going to get distance from the mean. So we subtract 9 from each of these things. And we get, these are our distances from the mean. Now we have these squared distances. So I take these numbers and I square them. And then we're going to do the, quote, average squared distance. So I'm going to add these up. And I'm going to divide by n minus 1. So here my variance is 2.5. And my standard deviation is going to be the square root of 2.5. So I think 1.29 something. Square root of 2.5, 1.5811. Okay, so indeed, when we calculated the standard deviation for the Baker family and the Thompson family, we see that the standard deviation for the Baker family is indeed greater than the standard deviation for the Thompson family. Okay? And so again, the standard deviation, the big picture right there is that it is just a number to quantify the amount of spread that we have in our data. Okay, we'll end there, right, for today's lecture, and we'll resume on Friday. So we'll see you guys then.